called theoretical strength of material, and that comes out to be G by 2 pi. Okay, so this is a very high amount. G of the order of 60 gigapascals will give you a strength of 10 gigapascal, and 10 gigapascal no material shows. So then we came to the understanding that things happen in a stepwise manner, right? And what are those steps? Those steps are formation of dislocation, not formation of dislocation. Dislocations are there already. The movement of dislocation. Okay. So when we come to the movement of dislocation, then there are two ways dislocation can move, and basically there are two types of dislocations which we read in, I shouldn't call it school days, but in preliminary studies of dislocation, we understand that there are edge dislocation and screw dislocation, right? But there are many other types of dislocations, and some of them we will try to understand today. Okay, there are helical dislocations, prismatic dislocations. We will see what are partial dislocations, okay, and why are they needed. Okay, so edge dislocation also we have discussed in the last class, and screw dislocation visualization is little different and also little complex. So screwed in edge dislocation, you have an extra half plane like this, okay, and I hope this also is not. So this is the extra half plane, and it moves with one step in the direction of this plane. So on this plane it is moving, this extra half plane. So when you have a shear stress, then this atomic layer will join this one and will become one, and the extra half plane, so this one will now become extra, okay, and this is how it will move. So this is known as Verger's vector, okay, so the vector in the direction of the slipping, okay, unit vector, okay, it's a unit vector. So in a face centered cubic structure, what do you think will be the magnitude of this vector? If we have a face centered cubic structure, what will be the magnitude? What will be this distance in an FCC?
Zero 0.21
unit?
Unit, I didn't remember it.
So what is it like? Distance you are giving me in angstrom or what? Meters, millimeters?
Yes, angstrom.
Angstrom.
Yes.
I am not too sure of that.
Yeah,
So in terms of lattice parameter, if you can tell me. So I know that for aluminum copper system, the lattice parameter is of the order of 4 point something angstrom. So if you are saying 0.2, then that doesn't appear to be angstrom to me, but I do not know.
About half of the lattice parameter.
About half of the lattice parameter. Why are you saying half?
Face centered, no?
Yes. So what is the reason that you are saying that from one atomic site to another atomic site, the distance is a by 2? It should be a, or why are you saying a by 2? A is lattice parameter, so you can try making an FCC, okay? So you just have to make cube and then you have atoms on the corners and you have atoms on the faces, okay? So what do you think will be this value? One step of dislocation movement. A by 2?
Root 2.
A by root. Why are you saying that?
Because plane in which it is moving is
And what is that plane?
111.
Good. So that's what I wanted you to know, that it will not move on the planes which you draw, okay? So this is a model of a dislocation which we were discussing yesterday, no? So you see, this is the extra half plane. This one. Okay, I don't have too many balls to make the whole crystal. And below this is missing.
Yes.
So because of that, you see the distortion I was talking about. This is the amount of distortion the lattice will have. Okay, so there will be a tensile stress field and there will be a compressive stress field. These atoms want to compress this one, right? And this wants to move them. Okay, if you have one stress field, for equilibrium you must have another one, right? And what is this red atom doing there?
Interstitial or?
Yes, it appears to be an interstitial because it is smaller.
Yes.
Okay, and we will understand why that is there. Okay, so in screw dislocation, the step formation is something like this, and this is the, so suppose, so I can draw like a cylindrical coordinate. Okay, so initially this, so now maybe you can visualize. Initially the upper surface was flat, okay, and then there is an elevation by a step, okay, and this step will keep on moving like a spiral, but the line of dislocation will be, so line of dislocation is which one? This is the line of dislocation, and this will be moving in this direction. Okay, so what is different in this case in comparison to that one is that in this case the line of dislocation is this and the movement is in this direction, so it is perpendicular to the line of dislocation. In this case it is parallel. Okay, because of this behavior, screw dislocations have least resistance in movement. Okay, because they don't need a plane first of all. So that requirement is not there, so that makes their movement very easy. And second thing is that edge dislocation has both stress fields of normal stress, so hydrostatic stress, as well as shear stress components. The stress environment which it creates causes both shearing and hydrostatic stress, whereas this one will not cause hydrostatic stress, it will only cause shear stress. Okay, and then you can imagine or try to make the octahedral voids which will be forming in an FCC. Okay, so you have face centered atoms on all the faces, and if you have to make an octahedral void, then how will you make it? Something like this, right? And you can make the same void in BCC also. So in BCC you will have here one atom, there one atom, right? So you will see that the distance from this atom to that atom is different from this atom to that atom. So that will cause, and there are atoms here. In FCC you will not have atoms there. Okay, so in BCC the void which will form will have a dilation in the octahedral void, will cause a shear stress. Okay, and that shear stress is going to interact with the shear stress of both edge and screw dislocation, because both of them have it. But if there is some obstruction which only has normal stress or hydrostatic stress field and there is no shear stress field, then it is not going to interact with screw dislocation because it doesn't have hydrostatic stress field. Okay, so those obstructions will be invisible to screw dislocation, and that's why screw dislocation can move very fast. Other understanding which you should try to visualize in edge dislocation, and the same concept is valid for screw, but visualization is easy in edge, so that's why we'll do that. So you imagine that this extra half plane is actually atomic layers, which you can see in that also, and you have atoms missing below. Okay, So if you put an atom here, then what will happen? So now we have to define a coordinate system. So let us say this is x, this is y, and this is z. Okay. So now let me name one unit distances in z with certain values. So this is z is equal to 0, this is z is equal to 1, z is equal to 2, and so on. Right? So on z is equal to 0, the dislocation extra half plane is until this distance on y. Okay? So if I define this to be origin, if this point is my origin, then this point is y is equal to -1, right? Or -a. So the extra half plane is until -a. But what happens to z is equal to 1? It is not there. It is at y is equal to 0, right? So I could put one atom there also, but then I don't put any other atom. Then what happens? The dislocation extra half plane definition is this for z is equal to 0 and z is equal to 1. And beyond that, now if I want to draw the dislocation line, then that dislocation line will look like this. Right? Now tell me how this thing will move. As long as it was just like that, it could move. Right? But in order to move for this assembly, this part also needs to move, although that is not on the plane. Right? If this is the Berger vector and this is the dislocation line, then it is still an edge dislocation. But the plane is not the slipping plane. Okay? The plane was that 1, 1, 1. Now it is perpendicular to that. So it is not possible for this thing to move. Okay? So now this part is pinned. This is nailed, crucified. Okay? And this phenomena will be happening at different locations. And you still are not stopping because why? Because you want to break the material. Okay? So what will happen is that you will have a lot of pinning at different locations. And then when you keep on applying the stress, these dislocation can still move. None of these markers are working. I have to get my own marker. So these dislocations will bow out like this. Right? Those parts which can move, they will move. Those which cannot, they are pinned, they are pinned. Right? And after a lot of shearing stress, it will become like this, and after a certain point, it will become like that. Okay? And the nature of these 2 points are exactly opposite, so they will merge after some point of time. Not point of time, but point of loading. Okay? And then what will you have? You will have the original dislocation as it was, and you will have another dislocation which is created. And it will not stop there because you are still not stopping. Okay? So again this will bow out and the same phenomena will keep on happening. So what is happening now is we are creating a lot of dislocations.